we had some discussion at dinner actually, and but now I forgot about it. So okay, I will have to. Anyway, let's go back. Maybe come back to my mind. Yeah, I think these are several remarks, and I repeat it again. You say, well, you gave few models. So why those models? So you see there were polynomial, there were quartic interactions, there were exponential, there were sine. You say, why those models? Why I cannot take other functions, analytic functions? You can do exponential, you can do polynomial. Why you cannot do analytic function? And I will say, well, try, and we will see. The point is, these are the only models we know how to study. Okay, this is all. Okay, this is like exploration of a territory. So you proceed by examples. We don't have a general theory. We cannot proceed top down because there is no definition. So we cannot state the definition and analyze the properties. We are still in this evolution of some conceptual field where the mathematization has no single out a good conceptual starting point. Okay, so I cannot tell you Markov process is this, a Markov field is that, because if I could try, I mean, people tried, but then there are 0 examples, so okay, you go back and you find a new definition. So at the end of the day, this is zoology, so now we are in this part of the field before Darwin, actually. So you look at some model, then you try to find similarities between models, and you hope that at some point there will be some clarity showing up. Okay, that's life of scientific. This is scientific research. Okay, it's bottom up. It's not top down. You're maybe from school you're used to top down. Okay, you give very nice definition, and then never apply. So you have to change them to apply to your situation. Okay, let's go back. Bezos spaces. So yesterday was claimed incorrectly that you don't know Bezos spaces, but since yesterday morning you know about Bezos spaces because all you have to know was written, more or less. I think I go back to the example of the delta function because it was a bit fast there. It seemed a bit magic, but somehow let's go back to Bezos spaces. I want to say. So this is a tool for us, okay? I don't study them for the sake of study them. I like analysis, but somehow for us it's a small tool. It's a convenient tool. It has a very nice intuitive property. It's very difficult to make big mistake where you use them, and we are not in situation where you need to understand very fine detail of the theory to be able to use it, okay? I remember the initial point was to decompose any distribution in some set. Okay, again, imagine, or this could be the torus or the full space again. It could be any manifold, but then it's a bit more complicated to define because here I'm using Fourier transform. Okay, so these are somehow I can be more precise now. You can imagine that. If you allow me to use Fourier transform, you look at the Fourier transform of your function or distribution, and then what you did, so this is in the dual space of your set, so this could be another torus or another full space, it's just the Fourier, the dual group associated to those. Anyway, Fourier transform, and then here you want to come back. So maybe you have a weight like this, and there should be some normalization factor. We don't care, but the point is, you don't. If you do this, you just recover the distribution of the function. This is the inverse Fourier transform, but you don't want to look at all. You want just to look at a piece of it, and here you put some weight. Rho I k. So remember, I is some number like this, and rho I k is just a function. Okay, the support of this function is some annulus. Okay, so you construct a nice function which looks like it has to be smooth, so it cannot be exactly the characteristic function of this set, but somehow is a nice function. This is for e bigger than 1, or is just a ball or radius 1 for e equal -1, okay? Because you are doing like an onion, no? You are familiar with onions. So you have onion, you have all the slices, onion rings, you fry, and you can, and then you have the core. So this is the core, and then you have a dyadic decomposition. This is maybe radius 1, and then you have 2, 4, 8. Okay. And you go on, okay? And then you have all these slices. And this is a nice analytic object. So now, the point, I think yesterday was a bit fast, but somehow the point is that, so this object, since it has act by multiplication in Fourier space, will act by convolution in real space. So actually this operation is convolution with some kernel. And this kernel in real space, it's in the full space. So if I do on R, because on the torus is a bit more complicated, but essentially on R, this looks like a given kernel, which is rescaled, and it is normalized in L2, in L1. Okay, so this kernel has to be normalized in L1. So you take a kernel, it's for I bigger than 0, since all these are like homothetic sets, so you can just take one and then rescale, and this kernel has this property. And this kernel is very nice, okay, decay very fast at infinity, it's smooth, whatever, okay. This is related to this is why you cannot choose the indicator function. If here you put the indicator function, then this kernel will be a very bad function, like imagine in one dimension will be like oscillating sine, which is not even in L1. So you cannot do that. You want a smooth things, which create a bit of a problem, but not so much. And Bezoar spaces are nice. Now you start to understand, because you can look at the same time at the Fourier transform and at the function. So you look at the real space, but you also know that each block does not oscillate too much. You see, if you take derivatives, you know that derivatives are defined and more or less can be bounded. We will see soon. So they are very. And the example for yesterday, so we take F to be the Dirac delta in 0. And then you see now, if I can be more precise why I did the computation yesterday. So the block is this will be just the convolution of this kernel with the delta function, but then the convolution with the delta function just pick up the value in 0. No, sorry, pick up just the kernel. So the delta function is the neutral element for this operation. And therefore, now these kernel are nice, but you see, so it's a rescaling of a given kernel. So when you take the supremum norm, for example, if you take the norm in L1, it's normalized. Okay, so this is what I was telling yesterday. If you look at this object in L1, it's normalized, so it's of order 1. And if you look at this object in L infinity, essentially here you don't see anything. You have to take the worst behavior, but this object is normalized, so it's scaled. So this is more or less to the ID. Okay, this is what I was saying yesterday, maybe and then you use the norm, and you see this is uniform in I. So in the second index of the Bezoar space, this is delta. So the second index of the Bezoar space, so you could say this is in B 0, 1, and infinity, because this is the best possible. You don't have to sum. You could actually, you cannot sum in I. It will not be in L1 in the I variable. So you have to take L infinity. So this is finite. Or you can say that B0. Sorry. Now here you have to take minus z to compensate for this, and then you have infinity, and again here you have to put infinity because you don't have any summability now. But again, if you want to lose a bit, you see you could lose a bit in this index and then gain some exponential decay to have summability. Okay, so is it in this space, but it could be in some space like B minus D. Then if you're willing to lose a bit, here you can even put L1. Okay? For example, okay? So all these norms are finite. So you see you lose a bit, then here you will have 2 to the minus epsilon I, and then you get summability. This is the best you can do. So essentially, but the second index is not very important, okay? We have to put there, but it's just a nuisance for us. In some problem of analysis, it's very important because you are analyzing a critical situation, but in our case, it will not matter. Okay, so remember, so just to recall you the norm, I use it several times, but this norm is just, you look at the blocks, again, LP, and this could be, okay, on the torus, only in the full space, and we will need weights, so I will do with weights later, and then 2 to the I alpha. Yeah, and then you measure, this is a sequence in I, and you measure the small L AQ. Okay, and then for probability theory, when you're using, there are details you have to know about if you want to work in this field, like especially in probability theory. We define, the convenient way to define these spaces is to take the space of distributions, Schwarz function. You compute the Fourier transform. You can always do this operation, essentially. So for any distribution, you can do that. And the point is, this number now can be infinity or not. And if it's finite, this is defined, this Banach space, okay? You have to prove it, but somehow that's the point. But this is, especially if you look at spaces like infinity, infinity, this will not be separable because you started from a too large set, is like L infinity, which is not separable. So you want to proceed differently, and maybe you want to take a smooth function and complete the smooth functions with respect to those norms. And in the case infinity, infinity, and maybe in other cases, but certainly in this case, you don't get the same space, okay? You complete the smooth function or you close the distribution, you get two spaces which are not the same, okay? This is like in L infinity, all the bounded function or the function of compact support which are you complete in the L infinity norm, you don't get the same spaces, okay? Because at infinity, the compactly supported function will always converge to something going to zero. Okay, so this is a detail. Then in probability theory, you want separable, otherwise you cannot do anything reasonable, so you want to proceed in the other way. But for us, it's not important. Okay, I need like maybe some time to tell you something about those spaces, so please ask questions, especially if this computation is not clear to you, maybe we have to go through, because then I want to do a computation with random functions, so it would be maybe like a more complicated version of this. Another fact, so you have nice embeddings. So you have this property of, you have a property of compact, yeah, I mean, these functions are very nice, so somehow they have smooth functions, and you can essentially compare norms in various spaces. So what you have is things like this. This is called like Bernstein inequality. Okay. Okay, so function which have localized Fourier support. You have equivalence of norms. So if you can measure LP norm by measuring another P, okay, so now I have to recall what I want to do. But you lose, okay? You can take P bigger than P prime, but then you lose, and you lose essentially 2 to the I. This is like Sobolev embedding theorem, so essentially you lose depending on the dimension of the space. So now I have to, this is like something like D to the, let's see, then I put, now I have to decide where to put the prime, so it looks like that, and you lose, so P is bigger than P prime, so 1 over P, yeah, is bigger, so I think it should be like that. Do you agree? Should be positive number. So P is big, yeah, I think this is okay, okay? So you have you can increase the integrability, but you pay irregularity. Okay, this is like Sobolev embedding theorems. Okay, I don't think it's difficult to remember. It's you have D, and then you have various things, and looks like that. Okay, it's compatible. It's compatible with this estimation, if you see. Okay, so here you go. If you want to increase from 1 to infinity. P prime, so P prime is L1, P is infinity. Yeah, so you lose D. You lose D in regularity. So it's compatible with this estimation of the delta function. So from this you can derive this by these kind of things, because this is true for every block, but then you rise at the level of the norm and you have a similar inequality. Okay, so I can increase, I will always, this is very important for us, so I will increase P by paying a bit of regularity. Okay? So Base-Day inequality implies a base of embedding. Which looks like Sobolev. Okay, I will use it essentially. For example, okay, you can say that the norm in B alpha PQ is bounded by there is a constant. Sorry, I don't trace the constant. The proof is not difficult. Okay, it's using essentially this thing. And then you use like Young inequality to estimate the convolution, and more or less you're done. Okay, you have to play a trick not to lose this delta here, so you put another convolution. But okay, I try to do it. Okay, you have to come up with a nice idea. Otherwise, it's easy to prove something like this, but you don't want that. Okay, so you have to use a trick. Try to find this trick. Okay, it's given that. Now you know everything, okay? This is all you have to know about this thing, more or less. I mean, what is not written on the blackboard is that you can do it in a way that this partition of unity exists, okay? And it should have other properties which you are not using right now, but we will use it later. So here I finished this estimate, so up to a constant, you can control that norm with another norm where you get higher P. So this is the same thing. You have P bigger or equal to P prime. You have higher P, maybe you keep the same Q. Of course, Q you can always decrease, okay? Because small L norm, so like small L infinity is controlled by small L1 because every element is smaller than the sum. So certainly you can always decrease Q. You can increase Q if you lose a bit of regularity, as I told you. So let's not talk about this. This is the important index P, and here you have to lose, and you lose as much. Okay, so you lose P prime minus P, which is positive, so plus actually. Okay, so this is a theorem which we will use to put here infinity and put there anything we like, and we will use it very soon. I think this is, let me, yeah, then I want to, yeah, okay, let me, then you have things like that. How about derivatives? So in this case, so I will use this notation. I will use this notation to denote a function. This is like here. It's a Fourier multiplier. So it's a function which acts as a multiplier in Fourier space. Okay, so let me write something like this. For me, it's the Fourier transform of this guy is just the Fourier transform of f times the function times kappa. Okay, kappa is the Fourier value. So this is a notation, just is a convenient notation. So with this notation, this is a definition. With this notation, for example, this operator is just rho I delta. Okay, so that's convenient notation. And then if you take a function which increase, let's say, which is bounded by 1 plus x with some let's say, some order m. So now if you have a multiply, these functions have to be smooth for other reason, but let's say, for example, you take a derivative, so a derivative you will have m equal 1. Okay, if you take the gradient, somehow correspond to one of these operators with m equal 1. And then you have a result like when you apply this kind of, it could be a differential operator, it could be an integral operator, okay? It could decay, so m can be any real number, okay? This is just telling you the order of this operator. And then when you apply to the function, this is, let me do it in this way to understand. Essentially what you can deduce is that when you apply, for example, to some LP norm, you see in this block you have only limited range of frequencies. So essentially the size of this operator it's given, so essentially you pay or you gain this factor. Okay, here if I is bigger than 0, because for the ball is a bit more complicated, you cannot gain very much. If m is negative, you don't gain because you are in the ball, so you don't have any estimate. But certainly for any annulus, you have an upper and lower bound, and so you can, well, let me say I have upper lower bound, otherwise it will not work for every m. But somehow you get something like this, okay? So you see derivative act like multiplication by a number. So this is what it's meant here. So it's very easy to estimate. Okay. Do you have a question? So if you take one derivative, so okay, let's take some consequence of this. If you take one derivative, so for example, okay, if you take the gradient of the function in some direction, okay, the gradient of the function in the Bezos spaces, Q, then this is bounded by the function, but you lose, you lose 1 degree of regularity. Okay, so it's very, very easy. Okay, so this is the gradient. If you do the same for the Laplacian, you lose 2 degree of regularity. Okay. Cannot be easier than that. Okay, you agree with me. Okay. If you take inverse of the Laplacians, if you take inverse of the Laplacian and alpha is negative, then you gain. If alpha is positive, you cannot gain much. Okay. No, actually, you gain in both cases. No, I think you gain in both cases. Sorry. You gain in both cases. Okay, you gain. Okay, and P and Q does not change, but then you can also change P and Q. Okay, so and all these are Fourier multipliers. Okay, in this case. Okay, so this is all I wanted to say. I think about Bezos spaces for the moment. Okay, then I think in the first week we don't need much more than this. Yeah, I will skip somehow I will. Yeah, maybe let me make another remark that they have an unpleasant feature that they are not comparable to Lebesgue spaces. Okay, so there is no combination of exponent. There is no combination of exponent which give you a norm which is equivalent to the Lebesgue space norm. Not even infinity, okay? Because somehow you measure the size of every block. So somehow you have inequalities in one direction. Let's say you F. Now I have to remember in which direction, but somehow F, let's say I control LP, okay? So if I control LP, I know that the size of every block in LP is bounded because this operator is normalized in L1. So by Young inequality, you can do that. But you see, now you lost information on I, so somehow you don't have any summability in I. And if you do in the other direction, so if you want to estimate the LP norm of F by the norm of the blocks, you use triangular inequality, so the only estimate you get is like that. And now you see that here you estimate the supremum norm in I, essentially. But here you need the L1 norm, okay? So there is a small gap of regularity, so you cannot close this. So essentially you have that. If I translate in our language, just exercise, so this is bit 0, P infinity is bounded by, well, up to constant, by LP, which is bounded by, unfortunately, another norm, which is bit 0, P1. Okay, so again, if you want to lose a bit of regularity, but usually maybe if you don't want, okay? So this is a bit of a nuisance, so I'm very, okay, this is the one negative point, yeah. Minus 1 I want to discuss. Well, you do as an exercise because it's a ball of radius 1. So if m is negative, you don't gain anything. But if m is positive, it's bounded. So somehow I just wanted, so this estimate would not be true for I minus 1 because imagine this decay very fast, but anyway, you are in a ball around 0, so you don't care how fast it decays. So this is not, you will not gain anything here. So I would need to take the positive part in that case. This, yeah, the ball around 1 is a bit special, so you have to think about it. But usually it's very simple because they're just a compactly supported in Fourier space function. So for example, if m is positive, this holds for every I, up to constants, of course. Okay. Yeah. There was something you was not. Yeah. Ball of minus 1 is put. They write minus 1 and non-zero because it's a special case. So there are Bezoar spaces which are called homogeneous, where you continue to slice at all scales, so positive and negative, but then they are a bit more complicated to handle because they don't see somehow distribution concentrated in 0 very well. But like polynomial, which are derivatives, whose Fourier transform are the derivative of the delta function, they don't distinguish very well because they're concentrated in 0 and they try to slice the region around 0 very thinly. But we don't need them, okay? So this is the only thing you need to be wary about, okay? And then, yeah.
I don't know, maybe like just to recall that when P is equal, P and Q is equal to 2 is a sum of.
Ah, yeah, good. Thank you. You have a good assistant today. This is a good. Also, the good news. So let's put it good phase. No, I have to write bigger. More. Okay. Yeah. Sorry if I forgot. I will try to. So the good news is that these are Sobolev spaces. Okay. Exercise for you. This is, in Fourier transform, you know everything, so this is an exercise. You have to use Plancherel on this side. You see 2, 2. 2, 2, this will become just a sum, and then you can do things. You can use Plancherel and identify. Okay, this is a good exercise. Everything, it's an exercise, okay? There are no difficult theorems. The point was just to find the right object to look at, and more or less all the properties are exercises which are not very difficult. So this is okay. I think here you just need a small idea, but I mean, Bernstein inequality require a bit of work, but it's okay. So if you assume this, all the rest is. Okay, I will try to write bigger, sorry. Okay, so this is tools we need, so let's go on. Let's try to use them to do something, otherwise, what is the point? try to compute, first thing I want to do is compute the regularity of the Gaussian free field. So this was, regularity of Gaussian free field. Now I'm kind with you, I do on the torus, okay? Then I will discuss what happens if you're in the real space. So I give you the ideas again, okay? Don't want, so we want to, so we need to understand, again, okay, so phi is distributed like the Gaussian free field on the torus, let's say torus in the dimension. So it's a simple object in some sense, okay? You can think of it as a sum of a bunch of a Gaussian. It's something like this. Okay, so you don't have to think it's a very complicated object. This would be the dual, the dual space of the torus. So let me forget the 2 pi because I will get them wrong. So you exercise for you, more or less the idea is that you get something like this, and then you have a family of complex Gaussian. And you have to define them in the right way, that is they have this has to be real, so somehow you want that they satisfy this property. So somehow the 2 Gaussian have only real Gaussians associated, okay? And G0 it's real. 0 it's real, it's a normal Gaussian, okay? Because you want this field to be real otherwise. And then you see, it looks like the composition of the Brownian motion, more or less, okay? Because this is 1 over n, and you have this, so whatever. And then we try to compute the size of, so we'll try to compute some base of norm. Actually, we want to control infinity, but the first computation we could do is try to estimate the size of this random variable. So this is a Gaussian random variable because it is a sum at a given point, and I take the block. So taking the block just restrict this sum to a subset because you have this function rho which appears. So we can try to do this. Maybe so if I do this, I will just rho I and some n, something like this around. And then you just restrict the sum on an annulus, so you have finitely many things there. And okay, and then you have to estimate this. Let's say I want to estimate this in L2, so I just want to estimate the size of this object, the variance, because it means 0. And you see from here, so this is, of course, all the Gaussian, they simplify, so you get only one single sum. You get rho square, and then you get 1 plus n squared. And n is sum in a set which looks like ZD. Okay, something like that. No, actually, I'm okay. No, there is something. I think I made a mistake in the notes. Oh, no, sorry, sorry, I was confused. I was thinking I was working on the lattice. No, okay, the dual space of this is D and then U sum. Okay, sorry. And essentially this computation is like this. So this is a sum. Remember that essentially the support of this function is the annulus. So essentially this sum is restricted to this annulus. So it's an annulus rescale to 2 to the I. And then we just have to estimate the size. So this set, so this denominator has a fixed size, okay? Essentially it's 2 to the I 2. So if I do this estimate, I get 2 to the minus 2i from the denominator. And then I need the volume of the region. the volume of the region is 2 to the I d. Finished. Okay, if I need an estimate, let's say I need an upper bound. So, okay, so this is essentially the size of 1 over 1 plus n in the annulus, okay? Because that's the point of taking this annulus. Essentially, you only have to take care of the magnitude of n, or the rest is irrelevant in the geometry. Then you get n is of size 2 to the I, because the annulus is of radius 2 to the I, so this gives you this factor with a minus, and then the volume of the region is of order 2 to the I, the dimension of the space. Okay, this is the volume of the annulus. Okay, so this is the volume of this rescaled annulus. Okay, so when I write this, I mean there is a model annulus, and then I rescale to be of size 2 to the I. So this is the computation. Okay, so I get this object goes like 2 to the I d minus 2. Okay, I have minus 2. You see, white noise would be like this. White noise would have a covariance which goes like 2 to the ID. And then I gain a factor 2 because I have the covariance which is the inverse of the Laplacian. So very easy. Okay, so this is just a covariance computation on a single variable. Okay, now you know from the theory, I mean, you have studied Brownian motion, you know that the size of Brownian motion in a point does not tell you anything about the regularity of the Brownian motion, but here we are using a bit of analysis to improve our understanding. So we know the size of the little Paley block in a point, so now we have to go from here to some estimate of the norm, okay? So the first norm that it's easy to estimate, is, now you have to be a bit smart. So the only thing you can do in probability is Fubini, okay? Once you know Fubini, you know everything. So once you know Fubini, you know everything. So you have to put yourself in a situation to use Fubini, and this is the right way to do. Okay, this is important, so let's, okay. So let me say something. This is something I say always to my student. If you do a proof, this is my way of looking at this problem, okay? So, but if I see a proof where there is a Borel-Cantelli, and to prove Borel-Cantelli you use Markov inequality, you're doing it wrong, okay? You're losing information in the process. Okay, so think about it. So we will, this is a case, but because usually when you prove Kolmogorov lemma, you want to use Borel-Cantelli and then do a Markov inequality, and that's wrong. Okay, I find wrong. So let's try to see here why. I will tell you later. So you will understand that at the end. Okay, so I want to study this. Alpha I don't know. I put P and I put P. So I want to prove that this norm is finite. So I want to prove that norm is finite almost surely. I want to take expectation. And if I get a finite number, it's almost surely finite. Okay, this is very easy. Now, why I want to do this? Because if you now write these norms, this is the expectation of what? Well, you have the power P of this LP norm. So essentially, everything disappears. You have sum over I. You have 2 to the alpha IP, because 2 to the I is the norm small p. And then you have LP norm on the torus, so which is an integral of the size of the little Paley block to the power t. And you see that this linearizes the full expression. Okay, that was my point to taking all the power to be the same. And at this point, you do Fubini to bring this here. And you're done. Well, we are not done because we have power p yet, so we're still not in this situation. So we try. So this is Fubini. This is the only important step. And then, so here, I have the expectation here. So, but this is a Gaussian random variable. So the expectation of the LP norm is comparable to the L2 norm to the right power. Okay, so here essentially modulo a constant. So let me just put less or equal, but is equal. Okay, is equal. There is a constant which depends on p. Sum over I, the integral over the torus, and then you have the expectation of delta phi x squared. Okay, of course, modulo a constant, the size of, the p moment is the variance to some power. Okay, so I just need to use the variance to the right power. Okay, by scaling, this is a computation with a one-dimensional Gaussian, okay, because you know the variance of this Gaussian, and then you compute this. Okay, we will need a more sophisticated argument in 15 minutes, but that's all we need for now. And then we are done. This I computed goes like that. So this is bounded by sum over I, the integral over the torus, and then here you have a number. This is translation invariant, so there were no x dependence anymore, important. So you get 2 to the, sorry, I forgot 2 to the I alpha, sorry. 2 to the alpha p, so here I have 2 to the I alpha p, and then I have 2 to the p over 2, I d minus 2. Okay, so this is the computation from that. So let me maybe write like this, it's better. You see, you have over 2 because a Gaussian is half of its covariance. Okay, this is very important. It's the square root of the covariance, the size of the Gaussian. Okay, so this is coherent. You have this divided by 2. And then you see that now I need to do this integral. So this is, I'm in good luck that I choose the torus because this is a finite integral. On the full space, this will not work. Okay, so this is finite, not on RD, so we will have to do something different if we want to do the full space, so we will see later. But bear in mind that at this point I'm using that on the torus. And then I have to sum over I, so I have to guarantee that this number is negative. Okay, so this is finite. Sorry. Well, certainly it's less or equal infinity, but I want to say less infinity, if, and only if essentially this, if, let not be ambitious, alpha plus d minus 2 over 2 is negative. Okay, so this gives you a bound on the regularity. Alpha can be smaller than 2 minus d over 2. Okay, it has to be smaller than that number. Okay? So this is all we. So this is, if alpha is smaller than that number, this number is finite. So what is our conclusion? Please ask question, okay, if you're lost. Yeah, maybe I stop a moment.
Why do we need the Bezos spaces here? Because we're only looking at the case where the exponents are equal, so it's order space, right? It's just a Sobolev space, right?
No, for p equal 2 is Sobolev space. Yeah. Good. I mean, if p equal 2, you can do a computation with Plancherel formula, because the L2 norm in real space is exactly the L2 norm in Fourier space, and then in Fourier space, this operator acts as some kind of partition of unity, so you get an 1 when you sum over all the pieces, and you get Sobolev spaces, but that's the only case. LP spaces, we have this sandwiching, which is not right, but I will show you, because I want to go, like Brownian motion, you know that the process is actually in older spaces, so you want to go to all this. This is old also for Brownian motion, by the way. Okay, this computation I'm not using. It will not be Brownian motion, it will be some strange of periodic Coste-Uhlenbeck process, but is at the same regularity of a Brownian motion. Okay, so you can do for Brownian motion, you just have to change the way the series work, but all the other computations are the same. So let me, now I will show you now why. So if you want to do in L2, yeah, sure. I mean, if I wanted to do with Sobolev space, then this is a computation you can do without Bezos spaces. Okay, if p equal 2 in this computation, you put 2, 2, 2. This is Sobolev space. You use Plancherel. You have a sum of Gaussian. You do a computation. You are done. and you can estimate, the regularity is the same, okay, to make the sum converge. At this moment I have this, so I proved that, so I proved essentially, well, you see, you don't only prove that this norm is finite, you have a bound on the moments, okay, so you see, if you do, well, here you don't need, but, okay. Okay, so we have that in particular, phi belongs to P alpha. So I write 2 minus D over 2 minus kappa. Kappa is a small number, PP, almost sure. And kappa for any kappa positive, of course, okay?
And also for any P.
Yeah, good, and for any P, good, thanks. Yeah, whatever. Any P large, because P can always be taken. Okay, so this is regularity of this field. This is, we cannot take infinity, but then you have this now not, so now I want to do a different, so I want to control the norm in infinity, so I will have be alpha infinity infinity. I want to control this. I still put P here, okay? And here, I'm just observing now that this is smaller than the norm of phi to the power P. Again, okay, I told you before that you can gain regularity if you lose integrability. So here you can put PP, because this we know how to deal with. And then you have to lose, well, you have to lose a bit for both indices, okay? So essentially, you have to lose, so for bringing infinity to P, you have to lose essentially D over P, okay? And for bring to bound infinity with P, you don't have to do anything, okay? Because here it's a summable function. You estimate every element of the function. So this is in the good direction. The other one, you have to lose a bit. Okay, so this index, you're saying in the blocks, the uniform size of the blocks is estimated by the LP norm of the blocks. Okay, so this is good. So you have only to lose to put infinity to P. Okay, so to go from here to here, you lose there. Yeah. Okay, so now you are done. So this is an older space, so you see, and this argument is deterministic. I'm not using any probability here, okay? Okay, so this is telling me that phi belongs also to C alpha. So this is always the same, so this will tell you also that phi belongs to this space minus kappa for any kappa positive. Almost sure, okay? So almost surely for any kappa positive. Okay, so you have this result. In particular, this gives you the regularity of, in one dimension, is like Brownian motion, okay? So for d equal 1, this tells you that phi is C1 half minus kappa. Almost sure. For, yeah, and you see. Okay, so for d equal 2, this is like Brownian motion, okay? And I didn't use any Borel-Cantelli, okay? No Markov inequality. Actually, you have a bound. The norm is bounded. Well, in this case, maybe it's Gaussian, so it's not very interesting. But in dimension 2, you see that d minus 2 is 0. So you have a distribution. We know already that it cannot be a function because the variance at a single point is infinity. But certainly it's a distribution of arbitrary negative low irregularity. Okay, so it's almost a function, it's barely a distribution. And in dimension 3, which are the 3 cases we like or we try to understand something about, these start to be very substantial negative, is minus 1/2. So this means that, so intuitively, it's the derivative of a function which is order 1/2. Okay, if you want to understand what does it mean minus 1/2, is the derivative of some order 1/2 function. And then in dimension 4, if you want to have, anyway, so this is -1 minus kappa. Okay, so start to be very negative, okay? So anyway, okay, so this is the first thing I wanted to do now. Maybe I want to spend, yeah. Okay, so this is why we introduce Bezos spaces, because we want of course, we could have used Sobolev spaces. I mean, you know, they're easy to use, but you pay a price. You pay a price that you don't see that the integrability is much better. Okay, integrability is infinity. If you start to use Sobolev spaces, you will have this function only in L2 kind of spaces. And then when you start to do computation, you run into problem. Like the cube will not be in any, you see, you lose integrability then if you start to take nonlinear function, while here it's in L infinity, so it's an algebra. Okay? Of course, you have to deal with the regularity, but somehow what I wanted to say is that the Bezos spaces for very little price to pay give you a lot of freedom to choose the right integrability. Okay, so and especially in stochastic analysis, it's a nice framework to prove regularity of stochastic processes. Okay, and this is more or less also what you do with Kolmogorov kind of theorem for Brownian motion, that you look at dyadic, somehow points at dyadic distance, and you try to do, so it's a bit different because we are using Fourier analysis, but conceptually it has the same flavor. Okay, so regularity of the Gaussian free field settled, okay, here. We go on, so now next thing to understand, so yeah, we will spend some time today, probably all the day, but try to understand now other properties of the Gaussian free field. So I will not prove that it's a Markov process because we will never be able to prove that any other things are Markov process. So you can look in the book of Berestiki and Powell to prove the domain Markov property. Okay, it's a distribution, so it's not clear what does it mean to restrict this distribution on the one-dimensional, even on one-dimensional smooth set. Okay, but somehow there is a trace, there is a notion of trace, and you can trace, and you can study the object at least in 2 and 3 dimensions.
Can you also do that trace in 3 dimensions?
I think you can, but yeah, I don't remember. I never look in the details. So, but I think you can. It's related. It's a Gaussian process which is related to the square root of the Laplacian.
Ah,
okay, so the covariance is like it's a Gaussian process with the square root of the Laplacian. It corresponds. Yeah, I mean, it's very interesting. So this Gaussian free field seems very simple, but those of you, yesterday somebody asked me, can you do the strong Markov property with the domain? So some people on the Gaussian free field, you can do complicated things like find a random domain to which you have this Markov property, but you cannot, this random domain, usually they looks like SLE paths. So there is a connection between the level lines of the Gaussian free field are SLE paths. Okay, so it has a very interesting geometry, which we don't care here. We have other direction to which develop, but essentially we did a lot of functional analysis, and the byproduct is that the only probabilistic thing you have to know is Fubini theorem. Okay. Okay. Now we try to understand. Remember our formula. So in our formula, we try to have a perturbation of the Gaussian free field. So let's go back to our formula. So we try to construct things like this, remember. This was the Gaussian free field. So this is the GFF. So phi is distributed like the GFF. And I want to construct some random variable here. Let's call it VT phi. A potential, and then maybe normalize. And the T stands for the regularization. So VT phi is my interaction potential, which looks like some function V, and then VTX dx, okay? I remember that this was just a regularization of the Gaussian free field. And now we could be even more precise, like RT, now that I have some technology. For example, you could take it just the sum or deletable Paley block up to level T. Okay, so you sum all deletable Paley block, but a finite number of them, then this function is moot, and this is a way to regularize. And this you can write as convolution with some function. Now I start to finish my letter, sorry. So this is convolution with some, let's call it theta. Okay, so convolution with a smooth function, which is, and the Fourier support of this smooth function is essentially, no, I don't want this, I want 2 to the I. Yeah, I want T to correspond, here is not very important, but later on I will use T to correspond to a scale, spatial scale, so I want all the index I so that the spatial scale is, is smaller than 1 over T, or bigger than 1 over T, okay, something like this. So the support is concentrated, is inside a ball of radius T. Okay, so essentially this. You take only frequencies up to T. Okay, so this is a smooth function. I can compute in a point. I can compute the potential, which is a nonlinear function. I told you that I need to take family of potentials because there is no chance to get a limit otherwise. And the point of again, I insist, the point of this representation is that this is a multiplicative, almost multiplicative functional in some sense, because the integral split in a sum and the exponential split in a product. And so it's important to understand, and here, the point is what can you put here? You want to put local functions of the Gaussian free field, okay? All this voodoo here is a way to produce local function of the Gaussian free field, because this is looking at the Gaussian free field essentially in a very small neighborhood, and then you try to do nonlinear operation with that and try to come up with something which is still nonlinear, but is local, depending only on the Gaussian free field data point. Okay, we are used to that. Okay, so Vt phi tx should converge to some local functional of phi, okay? Local in the intuitive sense that to know the value in a point, so this is, to know the value in a point, I should need only to know the Gaussian free field around that point, okay? This is locality is intuitive. I cannot do only the point because the Gaussian free field in a point does not exist, but certainly I can look in a neighborhood, okay? The point, I can look in a neighborhood of a point, radius epsilon, I look at the Gaussian free field and should produce this functional, let's call it V infinity phi infinity. Okay, so I should produce something that depends only on that point. Okay. So this is already for the Gaussian free field. This is the difficult question: is what are the local functionals of the Gaussian free field? Okay. So I cannot answer this question again. Yeah.
Regarding the modifier RT5.
Yeah.
This guy, in what space do he converges?
Well, it's a finite sum of smooth functions. So it converges in any space you like. Like Schwarz, like in the test function space. Yeah, because these are holomorphic functions, so point-wise, this is a finite sum, so there is no convergence actually involved. Okay, so yeah, this is a smooth. So RT send any distribution. Every block, little Pauli block, send a distribution in the test function space, holomorphic actually, even better. And then finite sum is, these are holomorphic functions of the space variable, because the Fourier support is bounded. So you can even extend to the complex plane if you want, okay?
I just wondered if
Analytic
in
function.
some base of space, but I think it's
Well, they said that this is a contraction in any base of space. Well, this is a contraction in any base of space. So certainly, if you look at the space where you have this regularity, this is also in that space, but it's better. But you can do any base of space. Okay, this is a good exercise, so let me maybe do it before. Okay, this is the important question. Let's not lose track, but you see, with all we know, it's an exercise to prove that this is infinity. So you can RT of phi, you can estimate be 1000. Infinity. Okay. This is bounded by what is the sum. Essentially, why I can estimate this? Because the Fourier support of this function, is bounded by t. Okay. So when I try to estimate regularity 1000, I can just write t 1000, and then the norm of this in essentially you have a result like this, and here you can put, let's say, well, I know this will have regularity, so 2 minus d over 2 minus kappa, so here I can put t1000 q plus t minus 2 plus kappa. Okay, so you have a result like this. This is maybe an exercise, but just to understand. Okay. Since the Fourier transport is bounded, imagine estimate regularity means you have to apply a differential operator of order 1000 to this function, and then estimate zero regularity. This is equivalent somehow. And then, essentially, because here contains finitely many Fourier Little-Wolf-Paley blocks, and then the regularity appear as a 2 to the I to the alpha. Now you have a 2 to the I to the alpha. My 2 to the I is always smaller than t because the support is bounded. So you have t to the alpha. And then you get something like that. Okay. Yeah, sorry for the silliness of 1000, but just to make a point. Okay, so it's you can be very precise how fast it diverges if you want to estimate a positive norm. This could be useful. So let's go back. Again, I cannot answer this question in full. There are other questions, maybe? No. Yeah.
After line, the Wi-Fi subscript what? Wi-Fi.
Phi.
Yeah, subscript.
This?
No. That one, there is, in the circle.
Yeah, sorry. So this I was saying, this was an image. Think about, so I want a local function. So I want a function at a point which depends only on the Gaussian free field in a small region around the set. Okay? This is the idea of locality. Okay, that this function should be measurable in this way. I will not prove it, but somehow the question of locality is which kind of function can I produce, measurable function of the Gaussian free field, which depend only on the Gaussian free field around a point. And then I don't have any particular answer, but I can produce example of those functions, and these examples are exactly the function you want to put here to create your new Markov process. Okay, so so let's go again. Okay, there is no general theory. I give you examples, then maybe somebody can prove that these are the only functions, but to my knowledge, there is no such theorem. Yeah. You see, this is a very difficult, it's a very interesting question. I find philosophically it's very interesting. Now you have you have a random field. Of course, you can compute at if it's a function, like temperature in every point, you can compute any function of the temperature and get a new random field at a new field. Now, a distributional field is more complicated because you don't see at any point, okay? It's like white noise. You don't know white noise at every point. And white noise does not have a lot of structure in some sense because at every point is independent. So what you want to be the functions. Okay. But Gaussian free field is more regular. So you are asking, okay, are there functions of the Gaussian free field which depend only, again, on this knowledge, on the randomness only in a small neighborhood. And that's an interesting question. Somehow, this gives you an algebra. Well, it's not even an algebra, but this gives you an interesting set of things you can observe about the Gaussian free field. Okay, these are all the local functions you can observe. So I give you examples. So I will introduce obvious answers, which are weak monomials. So you call them weak monomials, okay? Sorry, weak polynomial, weak powers, sorry. I'm a bit weak powers, okay? So this is an example of such local functions that you can produce. So let's define them. So I have to recall you have a notion of Hermite polynomial. Hermite polynomial are the orthogonal polynomial for the Gaussian, okay? For the Gaussian measure on R, okay, the Gaussian on R. Okay, so you have the Gaussian measure on R, and then you can construct the orthogonal polynomial in the L2 space of that measure. Okay, this is Gram-Schmidt. For any measure which good property, you can construct orthogonal polynomials. Okay, so you can do it for the Gaussian. And then if you are like me, you go to Wikipedia and you ask Hermite polynomial, and you get a list of Hermite polynomials. And you copy in the lecture notes, so you have a list of the first few Hermite polynomials, okay? Because I don't remember the coefficient. There is a way to reduce the coefficient, but... So Hermite polynomials are, we call it H1, X. X is just a real number because we are just looking at a single Gaussian, normalized Gaussian, okay? So you have this polynomial, the first one is 1, okay? They have to be a span of the space of all the polynomial smooth functions, okay? Then the first one with, okay, this is very boring, but start to be more interesting now. X2, now you have to find a polynomial of degree 2, so usually in probability we take them monic, so we take them, they start x squared, and then you do Gram-Schmidt with the other, and this is an exercise, and you try to find a coefficient of lower order which is orthogonal to those in the L2 space of the Gaussian measure, okay? So L2 space of the Gaussian, this is the normal 0, 1, and then this is exercise for you, and this is 1, you have to put 1, and then H3, so x cubed, and then, no, this I still remember is 3x, but then I start to, yeah, I think once I knew, but then, yeah, this I always get it wrong, so it's 6 and 3, so minus 6x squared plus 3, and you see there is some structure, okay, the even, the order of only odd polynomial, the even only even polynomials, and this coefficient could be computed by some combinatorics, but okay, let's forget about it. I will need essentially only these 4, but this will be very important for us. They play, because they are the seed from which we construct these local functions, okay? And these things we remove are this renormalization I was talking about, part of those renormalizations. Okay, so let's look. So this is just the structure of a single Gaussian, but then we will build up on this. And they have, so they are orthogonal, okay? So if you take a product of 2 and you take the average, you always get 0. And if you take 1 and you take the average, you get a number. So the only thing it's interesting is what you get when you get one of them. And this is the Gaussian. Let's say this is the Gaussian 0, 1 squared. So this is the variance of each of them. And then you get, Carlo, what you get?
Get the norm. You get
I think you get n factorial, yeah, thanks. But yeah. Okay, yeah, maybe another information. So this is what actually we need. We don't need it because we will ignore this number, but you can compute this. The idea, the general idea, which if you like, so you can look at Jenson's book. This is the standard reference, Gaussian Hilbert space. Okay, there are a lot of things. All you want to know, just you have to find it or about Gaussian, and there is this, and yeah, this I don't want to insist on the coefficient. We don't. Okay, for the moment we don't need. So let's stick with that. These are orthogonal polynomial, and you find everything in this book. Maybe another. If you want to generate them, they are generated by this series. Okay, you look at this function, you expand in T, and then this is the generating function. The coefficient of this expansion are the Hermite polynomials, okay? So in particular, if you want the exponential, is an infinite sum of Hermite. You see this kind of renormalized exponential that you are familiar with, maybe in Girsanov transform, you see that you have this kind. So this structure is that. And actually, okay, since maybe this is fun, I'm not sure we are using it tomorrow. Actually, I think we will use it next week. So maybe let me mention it. This is an interesting observation that if I now look at Brownian motion, so this is Brownian motion. No, sorry, what I'm writing. I know, yeah, it's correct, but for Brownian motion you have T only. Okay, so you see this is a Gaussian of variance T. If you put a Gaussian here. So this would be a Gaussian of variance square root of T, so I put only T here and not T squared. But then if you use the same formula, let me think a moment what I want to write. Yeah, this formula is a bit more complicated now. No, let me not write it, okay, actually. Yeah, okay, no, let me write it in this way. Yeah, sorry. So sum over n, this is n bigger equal to 1. And then I have, so I have t n over 2 divided n factorial, and then hn of bt divided square root of t. But somehow you don't have, you see this polynomial, this simplify, okay, write the first few terms. But this is a martingale, and essentially you will have all these terms are martingales, okay, in this formula. So there is a relation with stochastic calculus that is, if you do things correctly and you put the variance in the right place, because this is normalized to 1, but if you generalize to general variance, then you create polynomial of Brownian motion and T such that they are martingale. Okay, each of those objects is a martingale. And okay, so this is a martingale. And each of these objects is a martingale. Okay, anyway, if this was a curiosity, but we will use it later. And for Brownian motion, you can generate them by doing iterated stochastic integral on the Brownian motion. Then essentially, you see, this is the Ito correction term and things like that. Okay, so there is a relation with stochastic calculus. Okay, so once we have this, we have the good language to discuss what happens next. And what happens next is that now I want to create these weak powers of the GFF. And so my notation is this, but it's not universal. Okay, it's a strange power, or and this is defined as essentially the Hermite polynomial of the Gaussian free field, but with this definition you have to normalize, so it's the Hermite polynomial. So let's say, of course, Gaussian free field does not have value in a point, so let's take the regularization to start with. This is a very well-defined Gaussian random variable, so you put it here, you have to normalize, so here I put the covariance. Yeah, let's say in 0, and then you have to put the covariance outside again with the right power. This is a power n, so here you have n over 2. Okay, you need half of the covariance. So this is a definition for us. So you have, sorry, what is CT0 is just the expectation of phi t x squared. Okay, does not depend. Yeah, I mean, it's CTX, but somehow does not depend on x in the cases we are looking at, so we took it in 0. I should have taken it. Okay, let me be precise, but it's not very important because, yeah, this is the natural definition, let's say. And then because it's invariant by, I mean, in the cases we are considering, this does not depend on x. No, sorry. Yeah, no, sorry. Okay, let me, so, yeah, sorry. I said something wrong. So this is the covariance, and I call it CTX minus y. And here, just because I'm computing in the same point, I have that. Okay, sorry. Okay. Yeah, thanks. Square root. Yeah. So you want this to be of unit variance, and then, but all, yeah, when you look at these objects, it's clear, I mean, try to write them down, it's clear that the covariance replace, you see, here you have cubic power, here you have single power, so some by x squared has been replaced by its covariance, okay? So if you want to do with general covariance, like there will be a covariance function, and here you have the covariance, and you depend on the covariance, and here you have the covariance, and here you have the covariance square. Okay, so it's very easy to do the general ones. So this is our definition. You just take the Hermite polynomial of the regularized Gaussian free field at a point. So this is almost local, because this is just a small convolution. Well, in our case, it's a bit complicated, but somehow it's essentially local. This, in the spirit, is what we want. Okay, depend very, very little on very far region. So this is a new random field now that we constructed, which we are interested to understand. My point is that now, if I take t goes to infinity, this object will have limits. Okay, we'll define new random field. Of course, okay, so let's go. Let's try to see this. So this will be measurable function of the Gaussian free field, but will not be polynomial of the Gaussian free field anymore, will not be continuous functions, because the covariance has gone to infinity. Okay, so let me give you, again, let's write down the first few examples. So phi square, for example, this is phi square of x minus CT0. And let's say, I mean, there are at least a couple we have to familiarize with. So these two we will need. So let's write them. Here you have 3, and then CT0, phi t. Now the numerology is like how many ways you have to choose a pair here to create a covariance. Then you have 3, you have to remove those. Okay? And here the numerology is a bit more complicated, but essentially how many ways you have to take 2 among the 4, and then you have to compensate again. So this is, I could have just wrote down these 2 expressions without giving you the motivation why I choose them, but essentially the motivation is that. These are local function of phi t, and so almost local function of the Gaussian free field. And now I want to take t to go to 0 because I want really local functions, okay? That's the only requirement. That's why you have to remove the regularization, because you want this locality. Again, I insist about this. And you see that now CT, you compute it, so CT0, if you, I gave you the behavior of the covariance for the Gaussian free field, it diverges logarithmically. So when you regularize, here you will have a divergence, which is logarithm of t in dimension 2, and goes like t to the power d minus 2 in dimension bigger than 2. Okay? So in dimension 3, we'll go linearly. In dimension 4, we'll go quadratic. So you see that this polynomial, this nice function of phi t is not converging to a nice function of the Gaussian free field, okay? But the random variable will converge. Okay, and this infinity, it's called renormalization, okay? You are subtracting to phi square, you are subtracting a quantity which go to infinity. Yeah?
Can you explain one more time why the weak power is not a local function?
No, the weak power is a local function of phi t, but we're interested in phi. So what is the behavior? Phi is your basic field, you regularize it, you average a bit, and then this averaging is not allowed because somehow it prevents you to create really local functions. Okay, so you want to remove this averaging, you want to send t to infinity to get a local function, but then the price you have to pay is that this local function is not anymore a continuous function of the Gaussian free field in any way. Okay, so locality or nice, but not both. Okay, and renormalization, which looks, I think my message in this lecture, you have to understand that you have to renormalize to create this local function. Okay, that's all you have to do in life. A phenomenon you are familiar with is not equivalent because you don't subtract infinity, but you somehow you have to do something carefully. Is when you construct the Ito integral, you have to do adapted Riemann sums, like forward Riemann sums, and you know that you have to be very careful because if you don't do this, if you take the integrands in the future of the increment, or then you get a different limit. Okay, so somehow this non-robustness of this limit procedure become more complicated in higher dimension, where it's not the regularity that is lacking, but is even the fact that it's a function and become the origin of these infinite subtractions. Okay. Okay. So these are the objects. They are non-Gaussian. So we have to say something. Now I can run the same argument. That is, now I would like to show that these objects converge as a sequence of random elements in some base of spaces. Okay. So I will not prove the convergence, but certainly I will give you bounds so that it shows the tightness of the sequence of law of this random field, okay? And then I don't prove locality, but somehow locality is the main motivation, okay? I don't know any places where it's really discussed, but I think should be discussed. Maybe if I have some energy, I put something in the notes about that. Or maybe you can write a paper about locality of. I mean, to my knowledge, is not. I don't know any probabilistic. Maybe in the book of Powell, but one has to check. I don't know. I don't think they stress the locality of those objects. Okay, so we wanted the regularity of these guys. And now we proceed in the same manner, okay? Now you know everything because you know the tool. We want to use base of spaces. When n equal 1 is the Gaussian free field, this we already did. So when n is bigger, we want to do it. So in 2 dimension, it's easier. So let's stick in 2 dimension because you have this logarithmic singularity. It's a bit better. So the covariance at different points is just somehow is proportional to a logarithm of, let's say, x minus logarithm of x plus t minus 1. Okay, something like this. That is, if you look at the same point, you get log t. And otherwise, nearby points, they diverge logarithmically. Okay, if you send to infinity, you get. So somehow this is the regularized covariance. And then, okay, let me not, maybe because, I mean, on the notes, there are some more computation. I'm done with my time for today, so let me finish with this thing. we want to compute the regularity, so we are going to look at, so we run the same thing, so we take these weak powers, regularize, and we try to estimate uniformly in T, some base of norm, this will give tightness, and then convergence you have to control a bit better, but let's forget at the moment about, I will put alpha, and then I want to do infinity, so maybe C alpha with some power, let's call it P. So I want to control this, and then the argument is the same. You do base of embedding. And you put B alpha PP, and you have to lose D over P. Well, here D is 2, but let's say, well, let me keep D over T. And then you run the same proof, so I will not do. The only difference in the proof is that at some point we used that they were Gaussian when we were trying to estimate the P moment with the covariance. So you run the same proof. So there is only one difference, same proof, until you arrive to need to estimate the size of the little Pauli blocks of the weak power in a point x to the power p. Okay, this was the point where we used the fact that it's Gaussian. Now this object is not Gaussian anymore, it's a polynomial of a Gaussian. And here you have to use this other fact about Gaussian, which is called hypercontractivity. Are you going to do, okay, he's going to do for me, so I don't have to do it. Log Sobolev, you do log Sobolev. Okay, yeah, but we don't care, okay? This is technology people develop. Somehow what you have to know is that polynomial of a Gaussian, you can estimate LP norm by the L2 norm, like we did for the Gaussian, but for the Gaussian we know the law, so here we don't know the law, but it's a polynomial, and then the Gaussian spaces are nice enough that you can estimate hypercontractivity. There is a constant. This constant will be important later, but let's forget for the moment. I don't have, yeah, and then you just control the covariance. So the covariance look like this. And then you have to put the covariance by homogeneity to the right power. There is a constant, just know the constant very well, no? I need it later, so we will try to, I have a way to remember it, but I don't have time. We don't care now. Now there is a constant which depends on n, so this depends on p and n. You have to have a polynomial, does not work for analytic function, but for polynomial. Works also for function which, like Lipschitz function, I think you could have something, because it's, but okay, let's forget about this. Yeah, you have this, now you have to do a variance computation, and this is an exercise. I think I'm really over time now. No, I have 3 minutes, so technically, so we can do the variance computation. But this is the variance by scaling, essentially. Now you reduce to polynomial of a single Gaussian. Okay, now the problem is trivial. So we have to, so it's trivial, well, it's almost trivial. So you have this polynomial, remember, this is a polynomial of a Gaussian, then you take the little Pauli block, you take the square. So this is the computation we have to do now. You have to be careful because there are the little Pauli blocks. So these objects are not computed at the same time, and the same point in the square. So you have to expand the square. You will have two integrals. So this is at the point x, but then a little. So you have this kernel for the little Pauli blocks from x to y, and then you have another one. You have to integrate from x to y prime because you have two of them, and then you have the covariance of the weak power, which I didn't discuss, but somehow you have one weak power, another weak power in y and y prime, sorry. Okay, so you have the covariance of the weak power. And now, okay, I told you they are orthogonal, so we didn't compute this, but essentially by using the theory, this is just the covariance between y and y prime, so it's the covariance between the associated Gaussian to the power n. This we didn't do, but trust me that this is the case. So you just have to pair one Gaussian here with the other Gaussian there, they produce this, and you do for everything. And all the subtraction we did is to remove any other possible thing you should do. Okay, so you get very simple. And in our case, this is just a power of the log. So if you forget about t, you just get a log divergence on the diagonal, okay? And so you have to do an estimation here to estimate this integral. So let me skip about it. You have on the notes the detail. You have maybe in the notes, I just splitted the things using Cauchy-Holder inequality because the log is integrable, and then you have to estimate some power of those. Those are normalized in L1, but then when you take a power bigger than 1, you get some divergence because they're not normalized anymore. So you get something like 2 to the I from those. You get a small power. So let me, so you get something like this with epsilon positive small. Okay, you can do this for any epsilon. Okay, this is coming because you have a logarithmic divergence, so you cannot estimate easily. You cannot estimate them in L1. You have to lose a bit of integrability. But arbitrary small integrability, it's fine. And then it means that you see this will tell you the regularity now. If you remember how this entered into my computation, this end up to say that this is uniformly bounded. So I have, okay, let me stop. Okay, let me write, I have 1 minute, sorry, half minutes to write what we proved, and then I stop there, continue tomorrow. You have supremum over T of the expectation of the weak power renormalized in the base of norm B. Essentially, this means that you are in every small negative Bezos space. So essentially, we proved that if you put everything together, we prove that this is C minus kappa to power P is bounded. Okay, this is fine. This is for every P and every kappa small. Well, P has to be bigger than 1, of course. Okay, so we proved that. So this means that this sequence of random field is tight in a space or arbitrary negative regularity, independent of n. Okay, this does not depend on n. In dimension 2. No, this computation is in dimension 2. Okay, tomorrow I will give you a very sad information about dimension 3, but for the moment, let's be happy with that. Okay? And for any, we created many local functions, okay? Every of this field is a local function, so I will call it, the limit is unique, but we don't know, but essentially I will create the weak power as the limit of this sequence, okay? Like in law or pathwise, whatever. Now you created a new random field as the limit of this random field, and these are these are new random fields, but somehow they are measurable. They morally, I didn't prove it, but morally they are local function of the Gaussian free field. They are distributions, so they cannot be multiplied, so it's not easy to create other local functions out of them. But somehow the idea is that, yeah, the algebra of Gaussian free field is very complicated because you cannot just multiply things to create new local functions. Okay, it's not like numbers. Okay, every number you can multiply with every other number, but Euclidean fields you cannot multiply at the same point. What you have to do is you have to regularize, so multiply in nearby points and then take some limit, and then you have to renormalize. Okay, stop here. Thank you.